Today's episode of SpaceTime is brought to you by the Dollar Shave Club. Join the club and get a great shave at an even better price. And to let them know you came from here, use the link dollarshaveclub.com/space for a special offer exclusive to us. This is SpaceTime, Series 20, Episode 77. Coming up on SpaceTime, a rare meteorite rocking the scientific community, a new theory on the creation of supermassive black holes, and the record-setting Comet already starting to show signs of life while still well beyond the orbit of Saturn. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A rare meteorite discovered by prospectors in far north Queensland is providing new clues about the internal structures of large asteroids and possibly even some terrestrial planets. The 15-kilogram space rock was uncovered about 3 years ago, some 2 metres below the surface, by a couple fossicking for gold with a metal detector. After digging it out, they realised it wasn't their long-held dream of a gold nugget, but simply a rather unusually heavy rusty-coloured rock. However, things got a lot more interesting when they chipped away a piece off the end of the rock. The couple noticed its unusual structure of discrete grains a few millimetres across and contacted the Queensland Museum. It was there that scientists identified it as a rare dendritic iron trollite meteorite, one of only a handful of known examples around the world. Dr. Andrew Christie from the University of Queensland and the Queensland Museum, who's begun the task of studying the meteorite, says it's a really unusual type of space rock. In fact, there are only 5 or 6 examples of this specific type of meteorite in the scientific literature. Most meteorites reaching Earth are stony in composition rather than metal alloys. When Christie studied the meteorite, he realised it wasn't all metal as expected. Instead, it comprised a labyrinth pattern of silvery metallic crystals shaped like staghorn corals, with rounded fingers branching out into the surrounding bronze-coloured iron sulfide matrix. It seems as the metal cooled, it formed crystals growing into the still molten sulfide, which eventually solidified around the crystals. So, rather than a chunk of metal from the core of an asteroid, well away from any other material that wasn't metal, this sample seems to be the edge of a large mass of metal where the crystals have been encountering molten sulfide. Christie and colleagues also discovered that the metallic crystals weren't just a single iron-nickel alloy, but actually 2 different alloys. Crystals in the centre contained far more nickel, while those around the outer regions were richer in iron, where the metal composition changed as the crystals grew. The meteorite also displayed a very distinct pattern of interlocking metal crystals in angled crosshatch textures, indicating it cooled down slowly over time a long way from the Sun. The metallic crystals are encased in trollite, a rare iron sulfide mineral. Small amounts of trollite are not uncommon in meteorites, but in this case it's making up almost a third of the total mass. Most meteorites are smashed off the surface of asteroids during collisions, while the rest originate from the asteroid's core. But this rare dendritic iron trollite specimen is thought to have originated right on the core mantle boundary. One of the old ideas about the structure of the Earth was that there might have been a sulfide layer between the core and silicate mantle above it. That's no longer believed to be true for the Earth, but it's still possible for bodies found further out in the solar system, such as Mars, and certainly for asteroids. And this meteor, with quite a lot of sulfide and metal crystals growing out from the core into it, is proof of that. The meteorite is providing an opportunity for scientists to find out how different elements move from different regions of a growing body like an asteroid or a planet. Christie wants to determine the cooling rate at which the iron crystals were growing, and then tie all that together into a scientific paper, hopefully before the end of 2018. Iron meteorites come from the breakup of asteroids large enough to have undergone differentiation. There are still a lot of questions about just how big an asteroid or a planetesimal needs to be before it has enough mass to differentiate into a metallic core surrounded by a rocky mantle. Differentiation occurs because all the dust and other particles that accrete to become a planet or asteroid heat up both because of radioactive elements and simply because of gravitational pressure. As the accumulated mass continues to grow, it tends to get hotter and hotter in the middle, eventually getting hot enough to start melting some of the minerals. When this happens, the molten metal, which is both very runny and dense, tends to migrate towards the centre, forming the core, while the lighter, less dense rocky silicate material forms the surrounding mantle. An asteroid would need to be many hundreds of kilometres wide in order to differentiate. The 525 kilometre wide Vesta, which orbits in the main asteroid belt between Mars and Jupiter, is a good example of a differentiated asteroid. Christie says the prospectors were lucky to have found the meteorite.
It was discovered about 3 years ago, I think, by a couple who were fossicking for gold up in northern Queensland with a metal detector. Just below the surface of the ground, they found something substantial, which, when they uncovered it, turned out not to be gold. It was very heavy, obviously metallic, and had a rusty coating, suggesting it was very, very rich in iron. Once they extracted it, it was a boulder, something like about 35 centimetres across in longest dimensions, weighing about 15 kilograms. For a meteorite, that's really quite large. They were very early on attuned to the idea that it might be a meteorite. They had a bit of a hammer at one end and got off the rusty crust at that end, which was actually very useful when I had my first look at it. I only arrived on the deck at the Queensland Museum as curator of minerals just under a year ago, so I didn't see it until we'd already had it. They immediately appreciated the potential scientific importance of it rather than, sort of value as a gold nugget or anything. And we're very lucky that they brought it into the museum for study. So when I finally arrived on the scene and had a look at it, what I noticed is where it had been hammered a little bit at one end, the rust had flaked away. There's a bit of metal underneath which had started to separate into crystals, discrete grains that were about a few millimetres across. And that's something that you wouldn't see in a sort of man-made iron alloy item. Because, of course, one of the risks with sort of iron-rich chunks of metal found in the ground is there might be a bit of some old ploughshare or industrial machinery or something like that.
Or even some slag from something, yeah.
Exactly, yeah. And, people do find things like that and, bring them in. And, of course, we have to disappoint them and say, well, no, sorry, this one's man-made and definitely from planet Earth. But in this case, it was already at that point showing textures that you'd only really find in something that had cooled down very, very slowly in some body further out in the solar system and that had arrived on Earth from there. So we were quite excited about that, and they were quite excited about that. But the next thing you need to do if you're going to proceed with studying something like that is to get a look at what the fresh material looks like underneath the rusty coating. So we asked them if they would mind sawing the end off to get us a nice fresh cross-section through to see what the interior looked like and see what for instance, what textures of these metal grains there might be in there. Because something else that you find that's very, very characteristic of iron meteorites and cannot be replicated in any sort of laboratory grain material on Earth, very, very distinctive patterns of interlocking metal crystals called Bitmatchdecken textures. Look very much like a sort of cross-hatched or even sort of hexagonal pattern of sort of plates and laths of metal going in distinctive directions, making distinctive angles to each other. And most iron meteorites, you would expect to see those on some size scale or another after getting a nice flat surface, polishing it, and maybe a bit of gentle etching just to bring out the boundaries of the crystals a bit. So I was very, very surprised when we got back the meteorite with a sawn surface and a sort of thin sort of bread slice taken out of it, chemical analysis work and so on down the track. And it wasn't 100% metal right the way through like I've been inspecting. Instead, we had this absolutely beautiful sort of labyrinth-like pattern of metal crystals of a very different shape from what I was expecting. If you can imagine, more like sort of silvery metallic sort of stag's horn coral, sort of rounded fingers of metal branching out into a surrounding matrix, which is more sort of bronze-coloured iron sulfide mineral. And there are very, very few of these that have been known and well described and published around the world. I could only find, I think, good papers on about 5 or 6 of them. This is a nice large example. What we seem to have here is, rather than a chunk of metal right out from the the middle of a core of some asteroid well away from any other materials that weren't metal, we seem to have sort of the edge of a large mass of metal where the metal crystals have been encountering this sulfide, which would have been when it was all hot and the metal crystals were growing, slowly cooling down, the sulfide would have stayed liquid a bit longer, so they would have been growing into this sort of bronzy liquid sulfide, and then eventually that set solid around them. So it's a beautiful opportunity, a material like that, to find out, for instance, how different chemical elements would have sorted themselves out between the metal and the sulfide, which would not have been part of the, which doesn't make up, for instance, the core of the Earth particularly, and hence how chemical elements sort themselves out, distribute themselves between different bits of a growing body like an asteroid or a planet. So it's a great scientific opportunity, really, really interesting specimen to work on science-wise. Our good fortune then continued. Not only had the couple brought it into us, having appreciated its possible scientific interest, but the museum was then able to get a grant from the federal government's National Cultural Heritage account to help pay for it. That covered 50% of the purchase cost. So we've now been able to buy it from them. So they've been well rewarded. We've been well rewarded in that we now have this nice large example of a very, very unusual meteorite as part of the state's cultural heritage. And I've started doing some research on those pieces of it. So that's sort of where we are at the moment.
All right, so tell me about the environment where it was found.
There is certainly no large crater. Something this size, even though it's quite substantial for a fragment that's actually been found, wouldn't make much. Well, it wouldn't make more than a dent in the Earth, really, in its own right. The large craters tend to be produced by objects which come in so fast that they basically explode on impact. All that kinetic energy from their mass and their speed has to go somewhere when they suddenly encounter the Earth and stop. So it's really a sort of spherical explosion as they stop very suddenly that produces a crater which is much, much bigger than the object. An object a few metres across, for instance, could produce a crater that was as big as 100 metres just as a result of exploding like that. But this is quite a bit smaller than that.
How lucky were they to find a piece like this? Also, where it would have just blended in with everything else. I mean, we know that people are very fortunate to find meteorites in places like Antarctica or the Sahara because the rocks look very different from the area they're in. These are black things on a white, snowy, icy background or dark things on a yellowy, sandy background, depending where you find them. But a rusty-looking rock, that must have still been fairly fortuitous.
Oh, it gets even better than that. The places you mentioned, like Antarctica, the Sahara, and we actually have one of our own in Australia, which is the Nullarbor Plain, adjacent to the Great Australian Bight, straddling South Australia and Western Australia, are all very, very dry, flat, barren places without a lot of vegetation and a fairly light coloured background. So as you say, a black rock sitting on that stands out a mile and is very, very easy to detect and go and collect. The location where this one was found, firstly, it was as far as I can tell, it was completely underground, but within reach of their metal detector. Yep. Second, it wasn't in one of those dry, barren places, which, because of the lack of water, can preserve meteorites for a good long time. It was in the tropics of the Queensland Gulf country, so I suspect we're talking somewhere that would be fairly lush and green in the wet season. And a meteorite like that would tend to rust down and disintegrate really quite quickly if it hadn't been found and dug up. So from that point of view, they were very, very lucky. And it is quite unusual actually having a meteorite recovered from that sort of environment rather than from a drier, sort of more arid, poorly vegetated sort of environment.
What do we know about the history of dendritic iron triolite?
Really a sort of very special type, texturally, of iron meteorites. And in order to have an iron meteorite, you obviously have to have somebody which has somebody in the sense of asteroid or similar, which has a large mass of iron segregated out in it. That makes it fairly likely that we're talking an asteroid rather than something from further out, which would be more likely sort of made of sort of ices, sort of water ice and so on. And also the original parent body would probably have been quite big. I mean, most of the meteorites that do reach Earth are more of a sort of stony mineral composition rather than metal alloys. The only thing is, of course, they're not as easy to identify as meteorites because they look like rocks rather than large pieces of metal. And also they tend to disintegrate and weather down faster and rapidly become unrecognisable. The irons do actually last a bit longer. This would have been from some asteroid out there that was big enough to have developed a metal core, because they don't all do that.
So this had to be big enough to differentiate.
Some of the larger asteroids that we've studied well and have sent space probes to, like, for instance, Vesta, asteroid number 4, have very definitely differentiated a bit like that, because the rocks on the surface are igneous rocks, very similar to some of the igneous rocks on Earth. Others of the large asteroids still seem to have what we call sort of chondritic composition, with a sort of jumble of sort of clay minerals and all the little grains and droplets that would have been the material from which they originally aggregated.
Things like COA clasts and things like that.
Exactly, yeah. So they're still retaining the very, very old, very early small granular materials from which everything in the solar system was ultimately constructed, but that haven't yet heated up and melted and sort of changed their minerals yet. So we're talking something big enough to have gone through that heating and differentiation process. Then, in order to expose the metal core, presumably the parent body would have had to suffer so many impacts with other asteroids that a lot of that rocky mantle would have been chipped off, ultimately exposing the metal core so that bits of that could be broken off and catapulted into orbits, which eventually brought them into collision with us.
That's Dr. Andrew Christie from the Queensland Museum and the University of Queensland. And this is SpaceTime. I'm Stuart Gary. Scientists using computer simulations have shown how a supermassive black hole could be created from supersonic gas streams left over from the Big Bang. The findings, reported in the journal Science, shows how a simulated black hole could be the source of the birth and development of the largest and oldest supermassive black holes ever recorded. If correct, it's a significant breakthrough in trying to understand the origins of supermassive black holes. Stellar mass black holes are formed through the supernova core collapse of stars far more massive than the Sun at the end of their lives. But mystery has continued to surround the creation of supermassive black holes, the monsters seen at the centres of most, if not all, galaxies. Most debate about the origin of supermassive black holes centres around the question of which came first. Did the supermassive black hole form in the superdense centre of the galaxy? Or did the galaxy form around a pre-existing supermassive black hole? Recent discoveries of supermassive black holes located 13 billion light-years away, corresponding to a time when the universe was just 5% of its present age, pose serious challenges to current theories for supermassive black hole formation and evolution. The bottom line is, the principal mechanisms that form supermassive black holes and drive their growth are poorly understood. Theoretical studies have suggested that these black holes are formed either from the remnants of the very first stars in the universe or from the direct gravitational collapse of massive clouds of primordial gas. However, these theories either have difficulties forming supermassive black holes fast enough or they require some very specific conditions to work. In this new study, the authors were able to identify a promising physical process through which a supermassive black hole could have formed fast enough. The key was incorporating the effect of supersonic gas motions with respect to dark matter, that mysterious substance that makes up about 80% of all the matter in the universe, but which we can't see and only interacts gravitationally with normal matter. The authors' supercomputer simulations showed that a massive clump of dark matter had formed when the universe was just 100 million years old. Supersonic gas streams generated by the Big Bang were caught by dark matter to form a dense turbulent gas cloud. Inside, a protostar began to form, and because the surrounding gas provided more than enough material for it to feed on, the star was able to grow extremely big in a short amount of time without releasing a lot of radiation. Once reaching a mass of some 34,000 times that of the Sun, the star collapsed under its own gravity, forming what would have been an intermediate mass black hole. These intermediate mass black holes born in the early universe would have continued growing and merging together to become supermassive black holes, millions to billions of times the mass of the Sun. The number density of massive black holes is derived to be approximately 1 per a volume of 3 billion light-years on a side, remarkably close to the observed number density of supermassive black holes. You're listening to SpaceTime. I'm Stuart Gary. Hey guys, I've got the answer to make your life so much easier. Since joining DollarShaveClub.com, I don't need to choose between price and quality to get an amazing shave. In fact, DollarShaveClub.com is a no-brainer for an incredible shave delivered right to your door. DollarShaveClub.com delivers high-quality razors right to my home for a lot less than what I used to pay. And so once you join the club, there's no reason to deal with all that hassle of going to the store and buying expensive razors. Just go to DollarShaveClub.com and pick a razor that works for you from their amazing lineup of blades. Choose between 2, 4 or 6 blades depending on what's best for your skin and beard. That's all there is to it. It's that simple. So here's your chance to see why over 3 million members just like me love Dollar Shave Club. Right now, get your first month of the club for as little as $5. And after that, it's just a few bucks a month. And you know what? Dollar Shave Club is so confident of the quality and value of all their products, there are no long-term commitments or any hidden fees, so there's absolutely no reason not to join and try it out. Get yours at dollarshaveclub.com/space. That way they'll know you came from us and you'll get a special introductory offer. That's dollarshaveclub.com/space. NASA's Hubble Space Telescope has imaged the farthest active inbound comet ever seen. The comet, named C2017 K2 Pan-STARRS, is still a whopping 2.4 billion kilometres from the Sun, placing it well beyond the orbit of Saturn. Yet despite this distance, the comet's nucleus is already enveloped by a 150,000 kilometre wide coma, a fuzzy cloud of gas and dust generated by the warmth of the still distant Sun. The comet's been travelling for millions of years from its home in the dark, frigid outer reaches of the solar system, where temperatures are a chilling -440 degrees. The comet's orbit indicates it came from the Oort cloud, a hypothetical spherical region of interstellar space almost a light year in diameter surrounding the solar system. The region contains a mixture of billions and billions of comets, frozen worlds and icy debris. Some of them are builders' rubble left over from the formation of the solar system 4.6 billion years ago. The rest are objects floating around interstellar space that have been captured by the Sun's gravitational pull. The study's lead researcher, David Jewett from the University of California, Los Angeles, says K2's so far from the Sun and so cold, all the fuzzy stuff making it look like a comet isn't being produced, as in other comets, by the evaporation of water ice, but instead the activity is more likely to be the sublimation of supervolatiles, from solids directly into gases, as K2 makes its maiden voyage into the solar system's planetary zone and the warmth of the Sun. Based on the Hubble observations of K2's coma, Jewett suggests that the sunlight's heating frozen volatile gases, such as oxygen, nitrogen, carbon dioxide and carbon monoxide, which coat the comet's frigid surface. As these icy volatiles lift off from the comet, they release dust, forming the coma. Past studies of the composition of comets nearer the Sun have revealed the same mixture of volatile ices. Jewett says these volatiles are likely spread all through K2. Most comets are discovered much closer to the Sun, nearer to Jupiter's orbit. So by the time astronomers see them, these surface volatiles have already been baked off. That's why Jewett thinks K2 is the most primitive comet seen so far. K2 was first discovered back in May by the Panoramic Survey Telescope and Rapid Response System Pan-STARRS. It's a survey project of NASA's NEO, or Near-Earth Object Observations program, based in Hawaii. Jewett then used Hubble's Wide Field Camera 3 at the end of June to take a closer look at the icy visitor. Hubble's sharp eyes revealed the extent of the coma and also helped estimate the nucleus deep inside to be about 20 kilometres wide. This vast coma therefore must have formed when the comet was even further away from the Sun. Digging through archival images, Jewett's team uncovered views of K2 and its fuzzy coma taken back in 2013 by the Canada-France-Hawaii telescope. But the object was so faint back then, no one really noticed it. Astronomers think the comet's been active continuously for at least 4 years. That's because in the Canada-France-Hawaii telescope data, K2 already has its coma, and back then it was still some 4 billion kilometres from the Sun, somewhere between the orbits of Uranus and Neptune. Curiously, however, the Hubble images don't show a tail, the signature of comets, flowing from K2. The absence of such a feature indicates the particles lifting off the comet are too large for radiation pressure from the Sun to sweep them back into a tail. Astronomers will have plenty of time to conduct detailed studies of K2. For the next 5 years, the comet will continue its journey into the inner solar system before reaching its closest point to the Sun in 2022, just beyond the orbit of Mars. I'm Stuart Gary. This is SpaceTime. Ariane 5 has successfully placed 2 telecommunications satellites into geostationary transfer orbits. The 54-metre tall rocket blasted up from the European Space Agency's Kourou spaceport in French Guiana, carrying the Intelsat 37E and BSat 4A.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top. Allumage Vulcain, allumage des 2 EAP et décollage Ariane 239. paramètres à bord sont corrects.
And as the DDO calls out that all is working flawlessly on board, Ariane 5, right on time, begins her mission, lifting off with a lot of fire, carrying her 2 new satellites. The 2 boosters are providing 90% of our thrust right now. The DDO is saying all is fine on board. 776 tons is our weight, is our mass at liftoff. And to get that sort of mass off the ground, you need, of course, a lot of push. Ariane is burning 5 tons of fuel every second, 2.5 tons in each booster every second. And the core stage burning another 300 kilos of fuel per second. Ariane 5 now following the program, the onboard computer, which gives all the orders, including stage separations, which we're going to see in just a minute. We're in the first of 4 flight phases. Ariane, as she heads across the Atlantic eastward. Right now, the first flight phase of the single first stage engine and the 2 boosters are burning. The boosters will each consume their 240 tons in just over 2 minutes. They are the first to be extinguished. You'll hear that from the DDO.
Le pilotage est calme.
This first flight phase using both cryogenic and storable propellant, a mix. Cryogenic propulsion offers certain advantages over storable propellant, better, more precise performance. It can be turned off and on. Motors can function longer. Arianes 1, 2, 4 owe their success to storable propellant, not cryogenics.
Séparation des 2 EAP, la trajectoire est nominale.
The DDO has confirmed extinction and separation of the boosters on either side, the boosters falling away, the core stage continuing to burn. The boosters will fall 500 kilometers from shore in a protected area. French Guiana chosen in part as a base for its opening on the ocean, on the Atlantic, launches posing no threat to local population. The speed we need to inject a satellite is roughly 9 kilometers per second, 9,000 kilometers an hour. Our speed now is just over 2 kilometers per second. Our altitude is over 100 kilometers up. We're getting close to separation of the fairing. There we are.
Separation
is given by 2 pyrotechnic systems, one horizontal, one vertical. One half of the fairing falling away on the left, the other half on the right. We can separate the fairing now. Why? Because we're out of the dense layers of the atmosphere, over 100 kilometers up. Neither friction nor heating to disturb the passengers. We also discard any dead weight, so we can maximize the launcher's performance. Fairing weighs
La propulsion est nominale.
The countdown was a complicated process and a long one. Final countdown actually began about 11 hours ago this morning. We here saw only the final moments. First checks of the electrical services, for example, began 10.5 hours ago. Filling of the lower stage began 4 hours ago with the liquid oxygen, liquid hydrogen. Filling of the upper stage began 3 hours ago with the same.
La trajectoire est nominale.
Ariane 5 is the heavy lift launcher, remember. The 2 other members of the family, Soyuz, lifting middle-sized payloads, 2 and 3 tons, and Vega, the light lift vehicle for missions of roughly 1 ton. With its family of launch vehicles, Arianespace is the reference providing launches of any mass to any orbit at any time.
Le pilotage est calme.
Arianespace, part of Europe's space effort, which is a 3-way affair among Arianespace, ESA, the European Space Agency, and the French National Space Agency, CNES. Arianespace in charge of operating the family of launchers and of marketing the launch services and the Ariane program. ESA funding new programs, and CNES overseeing coordination of all space-based operations.
Arianespace Flight VA239 placed the 6,438-kilogram Intelsat 37E satellite into its geostationary transfer orbit 29 minutes after launch. The Boeing-built Intelsat 37E uses a BSS 702MP platform fitted with C-band, Ku-band and steerable Ka-band transponders, providing new generation fixed and mobile communications across the Americas, Africa and Europe. The satellite has a designed life of more than 15 years. The Ariane 5 then deployed the 3,520-kilogram BSat-4A satellite 18 minutes later. The Space Systems L'Oreal-built BSat-4A will provide direct-to-home satellite television services across Japan. The spacecraft uses an SSL 1300 platform fitted with 24 Ku-band transponders, capable of being reprogrammed in flight to provide high-definition 4K and ultra-high-definition 8K broadcast transmissions. The satellite has a design life of more than 15 years. The successful launch follows an earlier abort launch attempt last month, when an electrical issue prevented the twin solid rocket boosters firing after main engine ignition. Onboard computers automatically shut down the Ariane 5's main Vulcan engine as soon as the fault was detected. Arianespace has slated 12 flights this year, with flight VA239 being the 95th launch of an Ariane 5 rocket. I'm Stuart Gary. This is SpaceTime. A Russian Proton rocket has blasted into orbit carrying the AsiaSat-9 telecommunications satellite. The Proton, equipped with a Breeze M upper stage, was launched from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan. The 6,140-kilogram AsiaSat-9 was deployed into its geostationary transfer orbit 9 hours and 13 minutes after launch. Built by Space Systems Loral in Palo Alto, California, the AsiaSat-9 is constructed around an SSL 1300 platform fitted with multiple C, Ku and Ka band transponders. These include the first dedicated Ku band beam from Myanmar, a wider high-powered C band covering the Asia-Pacific, new Ku band beams for Mongolia and Indonesia, and 2 enhanced Ku band beams for Australasia and East Asia. The mission was the 96th Proton flight for international launch services, and the 416th overall launch of a Proton rocket. You're listening to Space Time. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with a science report. And the latest snapshot of Australia's drug problem has found that 1 in 5 people who regularly use ecstasy have admitted taking a drug of unknown contents. Findings by the National Drug and Alcohol Research Centre at the University of New South Wales found that almost half reported health problems and a quarter have experienced an adverse effect related to their drug use. 13% of those surveyed admitted using crystal methamphetamine in the past 6 months. People who inject drugs regularly reported high rates of ice use. However, the proportion of survey respondents who reported recent ice use fell by 5%, from a peak of 73% in 2016 down to 68% in 2017. The study also found that teenagers who drank to cope with anxiety or depression were 2 times more likely to progress to high-risk drinking once they reached adulthood. While more young people are abstaining from drinking alcohol altogether, 1 in 5 continue to drink at risky levels. Chemical evidence for what could be some of the oldest traces of life on Earth have been discovered in ancient rocks in northeastern Canada. A report in the journal Nature claims the newly discovered signatures belong to organisms thought to have lived some 3.95 billion years ago. If confirmed, the findings would be among the earliest known signs of life. The report adds to a growing body of evidence indicating the early Earth was teeming with a variety of life. The previous record for the earliest possible life involved the discovery of fossilised microbes from Quebec dating back some 3.77 billion years. The findings are based on radioactive dating through an analysis of carbon-13 to carbon-12 isotopes in powdered rock and in individual graphite grains. However, concerns remain about the accuracy of this dating technique, because rocks that formed billions of years ago have been severely heated and reformed, thereby making the geological context hard to interpret. Also, the chemical traces of life can be difficult to distinguish from reactions that don't involve living organisms. Sequencing and analysis of ancient African genomes suggests that modern humans first began to diverge as a distinct population between 350,000 and 260,000 years ago. The study, reported in the journal Science, confirmed that anatomically modern humans evolved in Africa, but placing the exact date's been difficult based on analyses of modern population genomes. Researchers examined genomes from 7 ancient individuals from what is now modern-day South Africa. 3 were Stone Age hunter-gatherers, while the remaining 4 were Iron Age farmers. The team analysed these 7 genomes, along with databases from both modern and archaic genomes from around the world. They focused on the relatively high-quality genetic information derived from a hunter-gatherer boy who lived in the Stone Age and was unaffected by genetic mixtures with humans from other areas of Africa and Eurasia. They then systematically compared his genome to the other groups. Comparisons of the ancient genome and numerous others across various regions and timescales consistently suggested that modern human populations diverged between 350,000 and 260,000 years ago. And that's also consistent with the fossil record. This is roughly half the time spanning the split of modern humans from Neanderthals and Denisovans. Also of interest, the authors found that 3 of the 4 Iron Age individuals also carried a gene variant that protected them against malaria, and 2 had a variant associated with resistance to sleeping sickness. On the other hand, the older individuals from the Stone Age didn't have any of these protective variants. Ancient DNA extracted from fossil bones and museum specimens has shed new light on the mysterious loss of the thylacine or Tasmanian tiger from Australia's mainland. A study reported in the journal Biogeography traces the history of thylacine populations over the last 30,000 years. The researchers found that a large and genetically diverse population of thylacines lived in western regions of Australia right up until their extinction from the mainland around 3,000 years ago, separated from the eastern population. The research team believe climate change from about 4,000 years ago, caused by the onset of the El Niño Southern Oscillation pattern, was the likely main cause of mainland extinction. The thylacine was a marsupial carnivore, now infamous for its recent human-driven extinction from Tasmania following the arrival of Europeans and their government-sponsored bounty hunting schemes. Thylacines once lived across most of the Australian mainland, but by the time Europeans arrived in the late 1700s, they were found only in Tasmania. And thanks to human greed, they became extinct about 150 years later, with the very last member of the species dying all alone in the Hobart Zoo in 1936. The researchers generated 51 new thylacine mitochondrial DNA genome sequences based on fossil bones and museum specimens. The result is the largest dataset of thylacine DNA to date. This provided the first genetic evidence that mainland thylacines were split into eastern and western populations across southern Australia before the last ice age peaked about 25,000 years ago. The DNA evidence indicates mainland extinction was rapid and not the result of intrinsic factors such as inbreeding or loss of genetic diversity. Researchers also found evidence of a population crash, reducing numbers and genetic diversity of thylacines in Tasmania around the same time. And finally for now, scientists have identified what they think is the brain's aha moment. You know, that sudden flash of genius you get when you become aware of information that solves a problem or provides an answer to a difficult question. The findings, reported in the journal Current Biology, when combined with previous research, provides compelling evidence that this aha moment, this feeling of having decided, pierces consciousness when information collected by the brain reaches a critical level. The results suggest that this piercing of consciousness shares the same underlying brain mechanisms known to be involved in the making of far simpler decisions. More importantly, the study offers researchers new hope that the biological foundations of what we call consciousness may now finally be within science's grasp. The vast majority of thoughts circulating in the brain happen well below the radar of conscious awareness, meaning that even though the brain's processing them, you're not aware of it. How some of that information bubbles into levels of consciousness, however, remains an unsolved mystery. But this new study provides a way to finally observe that moment in real time, and then hopefully applying those findings to understanding consciousness itself. The most complex thoughts that the human brain can experience, such as love, grief, guilt, or morality, can ultimately be boiled down to a series of decisions made by the brain to engage with the outside world. This is SpaceTime. I'm Stuart Gary. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.
SpaceTime was brought to you today by the DollarShaveClub.com, a quality shave for less. And remember to use our special link to get an exclusive introductory offer. That's DollarShaveClub.com/space.